Hello everyone, welcome to my YouTube channel. So in this lecture, I will teach about the nucleophilic and electrophilic addition and abstraction in the organometallic chemistry. So for a metal to bring about the reaction to organic fragments, both of them really have to coordinate. So in contrast, we'll see in the chapter how to a metal can activate an associated ligand so that a direct attack to the external reagent can take place on the ligand without mirror binding to the metal center. So here nucleophilic or electrophilic addition to the ligand which is directly bound to the metal center. So here the upcoming electrophilic or nucleophilic do not directly bound to the metal center, it will attack to the ligand with it directly to the bound to the metal center. So first we discuss how the types of reaction. So the attacking reagent is normally either an electrophilic or an nucleophilic. So nucleophilic attack is favored when the metal fragment is a poor pi base but a good sigma acid. For example, so if the complex bear a net positive charge on or electron weakened ligand, in such case one of the ligand is deflected the electron to some extent of the nucleophilic that can attack the L dash. So that means the nucleophilic attack to the ligand center is possible when the metal is electron deficient. That means the metal is a poor pi base, or if there is a ligand in the ligand framework that will withdraw the electron density from the metal center, so that will favor the attack of the nucleophilic to the main ligand center. So electrophilic attack is favored when the metal is a weak pi acid but a strong pi base. For example, if the complex has net anionic charge, low oxidation state, the anionic L ligand cells that are good donors. So the electron density of one of the ligand is changed by the back donation so that it now becomes susceptible to attack by the electrophilic. So that means the electrophilic attack case, the scenario is different from the nucleophilic attack. So in the electrophilic attack, metal should be in the low oxidation state or anionic charge. That means the metal should be more electron dense. So in that case, it favors the electrophilic attack on the ligand center. So two possible mode of nucleophilic or electrophilic attack is found. So the reagent can become covalently attached to the ligand L dash so that a bond is formed between the reagent and the L dash. In the case, the newly modified ligand stays on the metal and we have an addition. So when the added electrophilic is a proton, the reaction is normally considered as a protonation by the acid. So two possible modes. One is the reagent that is covalently attached to the ligand L dash, so the bond is formed between the reagent and L dash. So in the alternative case, the reagent can detach a fragment from the ligand L dash or even detach the entire ligand in which case the modified reagent gives the potential pair of the metal and we have an abstraction. So that means there are two possibilities. One case, the nucleophilic or electrophilic attack to the ligand center which is attached to the metal. So the one case the ligand maybe ligand is stay normally in the ligand framework and a new ligand form is formed. But in another case, the entire ligand or some part of the ligand is detached to the upon attacking of this nucleophilic or the electrophilic that will detach to the coordination side of the metal center. That case it will call a abstraction. So a nucleophilic abstract a cationic fragment such as H plus or Me plus, while an electrophilic abstract can end the anionic fragment that is HCl, H minus or Cl minus. So when the nucleophilic abstract H plus, we normally consider reaction is deprotonated by base and open the reaction with an electrophilic generate a possible charge on the complex, perhaps it for the substituted attack of by a nucleophilic. So some example is shown here. So here we can see that the nucleophilics tend to reduce the hepticity of the ligand for which they added because they displace the metal from the carbon to which the attacking take place, and we convert. So in this in that case, the nucleophilic addition, here the pyridine is attacking to this coordinated ethylene molecule. So here the this product is formed. So that means the nucleophilics tend to reduce the hepticity of the ligand. So who is that? Because they displace the metal from the carbon to addition takes place, and we convert the eta 5 L2X into a eta 4 ligand and make the net and ionic charge on the complex on mode negative unit. So for net change in the electron count is of 0. So that means for the nucleophilic attacks, the when the nucleophilic adapt to the metal center, that case the hepticity of the ligand is reduced and the metal on net negative charge on the metal complex is formed, and then but the net electron count is change in the net electron count is 0. So in general, the LNH ligand is converted to NN ligand, and the NN ligand is converted to Ln minus X minus 1 X ligand. So electrophilic region contrast tend to increase the hepticity of the ligand to which they add, and the electrophilic attack on the ligand give rise to a deficiency of the electron density on the ligand, which is compensated by the attack of the metal bond pair on the ligand. So that means the difference between the electrophilic and nucleophilic attack is that for the nucleophilic attack case, the hepticity of the ligand is decreased and negative charge is on the metal center. But for the electrophilic case, the hepticity of the ligand is increased and the net positive charge on the metal center. So this is the example of a electrophilic nucleophilic attack. So here this hepticity has 2. So when the upon addition of the pyridine, the nucleophilic attack on this ethylene molecule. So here the net negative charge on the metal center and this hepticity reduced to 1. And this is the example of the electrophilic addition. So here the H plus is the electrophilic, so it attack the this ligand moiety. So here the hepticity of the ligand is eta 1, but is converted to eta 2 upon addition of the electrophilic, and it will increase the net positive charge on the metal center. So in general, LNX ligand is converted to Ln plus 1 ligand, and Ln ligand is converted to LNX on ligand. So this is an example of nucleophilic addition reaction, and this is the example of nucleophilic abstraction reaction. So here nucleophilic abstractions mean here the one here this nucleophilic, here phosphine is acts as a nucleophilic. It abstract one photon from this one of the amino molecule. So here this carbon type phosphine intermediate form, and this form, and this is the example electrophilic addition. So here the FeCO3 complex, here this is the in the neta 4. Here upon electrophilic addition, the hepticity is increased, is converted to neta 5. Here total A1, 2, 3, 4, 5 neta 5 mode of binding and net positive charge on the metal center. So this is the example of the electrophilic abstraction. So here for this case, here this H plus is electrophilic that attacks to the OH molecule, and here the upon elimination of water, this ethylene alkene metal complex is formed. Here the hepticity increased and the net positive charge on the metal center. So this is the basic difference of the nucleophilic addition and electrophilic addition. So nucleophilic addition case, the hepticity decreased, and electrophilic addition case, the hepticity increased. And for nucleophilic addition, the net negative on unit negative charge is on unit negative charge is generated in the metal center, and the for electrophilic case, on unit positive charge generated in the metal center. So attack at the metal without the ligand open observed. So in the case of nucleophilic, this is simply the associated substitution. can lead by the displacement of the Pauling. So if the original metal complex is 16 electron, attack may take place directly on the metal center. If the 18 electron, the ligand must usually dissociate first. So nucleophilic is therefore more likely to attack the ligand rather than the metal. So if the complex is 18 electron. So here, so that means when the metal complex is already in the 80 electron, that means that is electronically saturated. So that case, normally the nucleophilic attack on the ligand center is favorable compared to the nucleophilic attack on the metal center. But for the 16 electron complex, the nucleophilic attack on the metal center may be possible. So in this case, here the pyridine is a 2 electron donor, but here this metal is in the +2 oxidation state. This is already a so here the metal is a 16 electron complex, but here the pyridine upon addition of the pyridine, this is 18 electron complex. And it is a platinum 4 complex. So here the attack on the metal center is not favorable. The attack of the ligand center is possible. So a pyridine potential 2 electron ligand, but it does not attack the metal because the 8 electron compound is of the favorable situation for the platinum 2. So if this, we have seen that attacking the ligand on the nucleophilic does not increase the metal electron count. So for the electrophilic attack, the situation is different. So as a 0 electron reagent, and electrophilic does not increase the electron count of the metal, where is the attack at the metal or the ligand. So attack at the metal is always possible. Alternative pathway even for the 8 electron complex. Of course, the large electrophile such as PSTC plus may have steric problems to attacking the metal directly. So for the electrophilic case, the attack on the metal center may be possible because the electrophilic already is a 0 electron reagent, so that will not increase the electron count on the metal center. So there is a possibility for the even for the electron complex, the attack on the metal center is possible. So as on electron reagent, organic free radical also give the addition and the abstraction reaction, but these reactions are less well understood. The radical addition and the abstraction also tend to occur only in the part of the larger reaction scheme in which the radicals are formed and quickly react. The attack of the nucleophilic at the metal have been discussed under substitution. We have also looked at the attack of the electrophilic or radical at the internal protection sphere. So now I will discuss about the nucleophilic addition to the CO. So CO is a very sensitive to the nucleophilic attack when put into the metal sites of the low pi basicity. On the such side, CO carbon is positively charged because the LM sigma donation is compensated not by the metal to ligand back donation. So the CO pi star orbital open attack to the nucleophilic. Yes, CO is a very sensitive nucleophilic to the nucleophilic attack. That means when CO bound to the metal center, so there is the electron sigma donation from the CO atom to the metal center. So that will create a net positive charge on the carbon atom. So that will not compensate by the back donation of the metal to CO. So that's why the nucleophilic atom is the CO atom is the of the carbonyl is prone to be the activated for the nucleophilic atom. So nucleophilic lithium region convert a number of metal carbon to corresponding anionic acyl. So the net negative charge now makes the acyl labile to electrophilic addition to the acyl oxygen to give the fissile carbene complex. So the nucleophilic attack on the carbonyl by a lithium region that will form a acyl region, so that will prone to attack to the electrophilic attack that will form the carbene intermediate. So that is one of the process to generate the metal carbene from the metal carbonyl. So this is the example here APCO5 that will attack by the lithium NET2. So from this acyl intermediate, so here this NET2 is act as a nucleophilic, so that will attack the carbon center. So from this one, so here negative charge that will form this metal bond. So next this OMe3O at electrophilic, so that will form this OMe as a carbene podal. So the cationic charge on MnCO6 plus makes it's much more sensitive to the nucleophilic attack than the MnMO CO6. So in case of hydroxide or even water can attack the coordinated CO to give an unstable metacarboxylic acid intermediate. So this decomposes to CO2 and the metal hydride by the beta elimination. So this can be synthetically used for a very way to remove CO from the metal, something that is difficult to do it other ways because the CO can be dissociated is one of the most tightly bound metal complex. So here by using this strategy, the CO dissociation from the metal center is possible for so here the water molecule is attached to the CO molecule to form this intermediate where the upon a elimination of the hydride. So from this acid type intermediate, so that is a very unstable intermediate that will dissociate the CO2 to form this metal hydride to upon the beta hydride elimination. So this is the one classical example to dissociate of the CO to form the metal hydride intermediate. So the nucleophilic attack of methanol instead of water can give the metal ester, which is unstable because it has no, which is stable because it has no beta hydride. So now the displacement of Cl is favored in the first step over the displacement of PPH3. So this is the one example. So here this platinum. So here the displacement of the Cl is easier compared to the displacement of PR3. So this is the consequence of the polar solvent used and the steps of this step for the subsequent nucleophilic attack. By putting the net positive charge on the complex end, would activate the CO, and acid can reverse the addition reaction by protonating the methoxy group, which leads to loss of the methanol. So this is one of the course. The methoxide abstraction reaction is an example of the nucleophilic addition being reversed by the substitute electrophilic abstraction. So this is common. So that means that the product of an addition reaction may be decomposed via inverse reaction if unsuitable workup conditions are used. So for example, the product of the nucleophilic addition may revert to the starting material, and if excess acid is added to the reaction mixture with object to neutralize the excess nucleophilic. So here the upon ligand substitution of the CO, this cationic intermediate is formed. So upon this in the methanol medium, the methanol reacts to the nucleophilic to form this intermediate. So we saw that the ET3NO as an excellent agent for removing coordinated CO from the 18 complex. So the very nucleophilic oxygen is capable by attacking the CO carbon to give the species that can break down to 83N and CO2. The corresponding 16 electron metal fragment. That's how the cis disubstituted product is obtained because of the CO is transferred to another CO is laid back donation from the metal, hence are more activated toward the nucleophilic attack at carbon. That is the cis trans with PR3 pi acid PR3. So unfortunately, the amine form can sometimes coordinate to the metal if no better ligand is available. So a second problem with this method is that successive carbonyls become harder and harder to remove as the back donating of the remaining CO group increase because of their sensitivity to the nucleophilic attack decrease. So we are usually unable to remove more than one CO in this way. So here the ET3 is a good as a good nucleophilic which can remove the CO from the metal carbonyl is another example. So here only the possibility of one successive CO elimination is possible. So more than one is not possible. So this is the example. So here the ET3NO, the oxygen carbon is a nucleophilic that will attack to the carbon center. So from this intermediate, so upon elimination of the CO2 and NH3, this unsaturated metal intermediate is formed. So that will coordinate to the NH3 or the impedance of another ligand to form this saturated metal intermediate. So isonatyl complex are also more easily attacked by the nucleophilic than the CO complex, but the isonatyl is tend to bind higher oxidation of the metal where the back donation is less effective and final product is carbon. So here also for the isonatyl case, the nucleophilic attack is possible. So here this carbon atom is prone to attacked by the nucleophilic. So this intermediate form. So upon then this carbon intermediate is formed from this isolated complex. So here in the summary, the nucleophilic attack at the ligand is favored when the metal is a weak back bonder, and the electrophilic attack is performed when it is a strong back bonder. So in an addition, the reagent stays in the coordinate sphere. In the abstraction, the reagent abstract a ligand on the ligand fragment from the coordinate sphere. So next, I will discuss about the nucleophilic addition to the poly or poly ligands. So some poly is free state, such as benzene, ethylene, normally undergo electrophilic, not the nucleophilic attack. It is measure of the power of complexation of the alter the chemical character of both these polys as the ligand becomes sensitive to nucleophilic, inert to the electrophilic attack. So that means when the poly or when the alkene moiety is in the free state, there is a more electron density that will not nucleophilic attack is not favored. For this case, that case the electrophilic attack is formed. But when this is bound to the meta center, so they are too activated towards the nucleophilic attack that will alter the chemical behavior of this poly. So that phenomenon is called the unplug. So that will reverse the chemical character of compound is not known as a unplug. So if we are interested in inhibiting the electrophilic attack, the word regard at the metal as a protecting good. On the other hand, if we are interested in putting the nucleophilic attack, we should regard the same metal from it as a activated group. So in the vast majority of cases, the nucleophilics add to the face of the poly opposite to the metal. So since the metal is likely to have bound to the at least in that face of this free poly, so we may therefore see a selective attack of the nucleophilic on what was more interface in the free poly. So this is often useful to organic synthetic application. So now we will discuss about the Green-Davis-Mingus rule. So it is not usual for a single complex to have several polyene or polynyl ligands, in each case, we often see a selective attack at one side of the ligand only. So in Davis-Mingus notified certain pattern in this reaction. So from then the diverse set of rules that is usually allow us to predict the site of addition. So by this rule notified us that the which side of the addition to attack on the polyenes or polyenes. So from the rule one, the polyenes that is even or Ln ligands reacts before the polynyls that is LNX type ligand, and the open ligand react before the closed one, and the open polyenes terminal addition in all cases, and the open polynyls usually terminal attack, but the non-terminal if LNM is the electron donating. So now I will discuss about all these rules. So first rule one is the open polyenes react before the polynyls. So rule one takes the precedence over rule two whenever they conflict. So polyenes or even ligands are simply bonds having an even electron count on the covalent model. So odd ligands have the odd electron count. So closed ligands are ones like the CP, in which the oriented pi system and polyene or enil is conjugated in a ring. So open ligand like allied, the conjugation interpreted. Some ligand of the constituent according to this rule are illustrated. So here, so this is cyclobutadiene, this is the even, and the open polyenes. So this is a odd, and open polynyls. This is a even as closed polyene. So this is the odd and closed polynyls. So in this diagram, 6.8.9, so shows the rule in action. So 8.6, for this complex, the addition of variety of nucleophilic take place at the arene ring, as predicted by the rule one. The second nucleophilic can also add part to the other ring as the predicted by this rule one. So this polyene is attacked. So here the two nucleophilic can attack, one from first at this one, then this one. In the 8.7, we had a possibility from three Pauline and Pauline. So here the from the first rule, the open one will shows the addition takes place to the event and open butadiene ligand run to the event or closed a ring. So according to the rule 2, here this ring is going to be the nucleophilic attack. So in this case, this is a open, this is a closed and even Collins, and this is a open and odd polynyls. So here, according to the rule 2, the Collins are attacked to the rule 1. Collins will be attacked first when compared to the polynyls. So here, the attack here. In this case, it is an odd and closed system. This is an odd and closed system. So only happens if there is no other pi domain in the ligand present. So CP is stabilizing the ligand in studies on the nucleophilic attack because the CP is very sensitive, resistant to attack. Therefore, the direct addition to other ligand present in the metal. So in this case, we can treat the alkene and alkyne parts of the bis-cyclodiene as a independent entities. So even this is the even one, this is the odd one. So here the attack on the even one is take place, then the odd one, and this 8 point, and for these two cases it is a open and odd, this is a odd and closed, and so here according to the rule 2, here this open and odd will be first attack to the, and for this case this is a even. So here the nucleophilic attack will be formed. So although the rules were first developed empirically, and the MO study has shown that the open successfully predict the location of the atom having the highest efficiency of the LUMO under kinetic control, we should extract the addition at the point where the empty extractor orbital is the largest. So quantitatively, we can understand the rule as follows. So ligand having the higher extractor will tend to the more negatively charge, and therefore will tend to resist to nucleophilic attack relative to the L ligand. So the coordinated allylic group such as L2X ligand has more anionic character than the ethylic L ligand. So the picture even predicts the relative reactivity of the different ligand in same class at a point not converted by the groups. So for example, it is found that the pentadiene, which is a L2X type ligand, reacts faster before allylic LX. So we can understand this is because the former has a lower pi X character, the ethylene reacts before butadiene, and the LX2 is form is always a significant contributor to the structure of the butadiene complex. So the reason of the terminal carbons of the event open ligands at the site of the addition is that the coefficient of the LUMO are the larger there. So example, look at the side 3 of the butadiene. So an odd and open polynyl gives the terminal addition only if the metal is sufficient electron weight reference to the MO picture of the allylic group. We show that usually the LUMO is the side 2 has a large coefficient in the terminal, but the side 3 is a large coefficient at the central carbon. So as we got a less electron withdrawing metal, we tend to fill the side 2, and the extent that the side 3 becomes a low new LUMO. So we may no longer see the terminal attack. So example of the non-terminal attack, the allyl is shown. So here, so normally for this event case, the terminal attack is formed because from the MO diagram, side 3 is the LUMO. So here nucleophilic attack is the electron come from this side 3. So here this has the more terminal character. So that's why for the event case, the event and open ligands, the terminal case is formed. But for this odd and open polyps, the many times the terminal or the middle carbon is attacked. So here this electron withdrawing when the, so here for this case the metal is nucleophilic attack at this carbon atom to form this metal complex. So it is surprising that this Simpson's rule does so well in most cases. The situation can sometimes to be more complicated. So here the methoxide ion attached at every possible side, as the mixture is warmed at 80 degrees C to room temperature. So initially the addition takes place at the metal, and later the CO and C5 side, and the reaction we carried out above 0 degrees C. The normal product would have been observed, and that the complication would be escape detection. So the substituted on an arene tend to direct addition in way to one might expect. The electron releasing substitution usually direct attack the beta and electron attacking ones, the ortho rather than para, the perhaps because that puts a Q on the terminus of the configured system, resulting open poly. So the arene chromium tricarbon have been studied intensively with regard to the cation and nucleophilic. So here this molybdenum CO3, the worm is a nucleophilic that will attack first to the metal center in the lower temperature, but for 0 degree centigrade temperature, it may attack the carbonate carbon, and upon increase the temperature, the attack on the arene moiety from to this is a thermodynamic product. So the cyclohexadiene complex react with the nucleophilic to give 1,3-diene complex. An example is shown. The arrow refers to the point of the attachment for nucleophilic to the Pauling ligand. The synthesis of starting complex by electrophilic abstraction is also shown. This activates the ligand for the nucleophilic attacks. Once again, the directing effects can be used to the advantage. A 2-me substitution direct attack at C5 position of the cyclodiene, for example. So here, this electrophilic attack on this it abstract the proton. So here this density is increased, then the nucleophilic attack to this carbon to form this intermediate. So diene complex gives allyline on the nucleophilic attack. So note how the cis-wide conformation of the butadiene gives rise to the anti-methyl allyl nomenclature of the allyl complex, and substitution considered as a syn or anti with respect to the central CH position. The amine sector is a carbon, not as a nitrogen. So here is an example where this molecular complex upon addition of the H minus, so that will here from the neta 4 to this neta 3 allyl complex is formed. So here this amine is attacked to this cyclobutadiene to form this intermediate. So neta 3 allyl also be readily attacked and is activated toward the nucleophilic attack by the substitution of the bromide ion with CO, which is give back the net positive charge. The nucleophilic acts selectively on the end of the allyl CH2MO. So here, this is an example where the neta 3, here this neta 3 is the attack activated toward the nucleophilic attack by the substitution of this bromine by this CO with nucleophilic attack to this metal center. So this gives the control over the stoichiometry of the product, which can be resolved thanks to the presence of the optical active group are test on the CPD, which can carrying out the addition with unenantiable to the metal complex, means that the new asymmetric center on the ligand is formed with a very high asymmetric induction. This reaction therefore constitutes a chiral synthesis of the alkene zone. So next we will discuss about the Walker process. So the alkene complex undergo nucleophilic attack to give the metal alkyls, which can open reagent to give other products. So this is a basic important and industrial process. So the Walker process now used to make the 4 million tons of APR aldehydes from the alkenes. So the fact that the aqueous PDCl to oxidize the ethylene to acetaldehyde. Since the 9th century, the reaction consumes the PDCl2 and deposit metallic PDCl. It took the considerable imagination to see that the such reaction might be useful for the industrial scale because the PDCl2 is far too expensive to use the stoichiometric reagent. So in synthesis, the key in the catalysis is that PD to be recycled almost independently. The Walker realized that let's say it is possible to interpret PD0 before it is a chance to get precipitated by using copper chloride, which reoxidize the palladium and instead reduce the corpus chloride. This is the air sensitive and the dioxide back to the copper 2. The resulting set of the reaction is alternative eligible simple solution to the problem which resemble the coupled reaction, the biochemical catalysis. So Walker process here, the in palladium 2, palladium 2 is converted to palladium 0 and the ethylene converted to aldehyde. Again, this palladium 0 is converted to palladium 2 by the reduction of the copper 2 to copper 1. Again, this copper 1 is already oxidized in presence of water to form this 1 copper 2. So the equation, this is the equation. So the equation implies that the complex is going from this normal state in the solution, PdCl4 minus. This equation implies that it is going from a normal state of solid PdCl4 minus to the transition state of the source type of the reaction has gained C2H4 to loss of 2 Cl ions in a proton. We originally argued that the proton must be lost from the chlorinated water. So the palladium OH C2H4Cl2 is invoked as a key intermediate. It was assumed that this might undergo liquid insertion into the palladium OH bond, or the OH might attack to the chlorinated ethylene as a nucleophilic. The resulting hydroxyl ethylene palladium complex might be vinyl hydride elimination to give this vinyl alcohol, which is going to protonise to the acetaldehyde. So in fact, the mechanism is wrong. Something that is only discovered 20 years later as a result of the substitution by the, according to the original intermolecular mechanism, whether the reacts goes by insertion of the nucleophilic addition to the coordination OH, the stoichiochemistry at which the case of carbon of ethylene should be remain unchanged. This can be tested if you teach C star the alkene and the trap intermediate alkyl. We have trapped the alkyl because the rearrangement of acetaldehyde destroys the stoichiochemistry information. So this equation shows one way the trapping the alkyl uses the CO. We can see that if the hydroxyl carbonated OH group can travel back and affect the nucleophilic abstraction of the acid to give the free lactose. The stoichiochemistry of which can be determined by number of methods, including NMR and the microwave spectroscopy. In fact, the stoichiochemistry of the two carbons in the product is not the same that of the starting material. So here, this palladium bounded alkene moiety and the OH. Here, this insertion of the OH to this alkene moiety to form this intermediate. So upon CO insertion to form this one, then this attack to the carbonic carbon to form this one. Next possibility is the palladium. Here the nucleophilic attack of the water molecule of the alkene moiety to form this, then CO inserted to form this one, then from the currently expected mechanism involves the attack of the free water molecule from the solvent of the coordinated ethylene. So equation shows how this inverted the stoichiochemistry at one of the carbon and opposed to the one insertion mechanism. The loss of 2 Cl ions remove the anionic charge of the metal, which would otherwise prevent the nucleophilic attack. So the implications of even how the understood. So this mechanism implies that the water terms should be present in the reactive equation. So if it could not be seen, the mechanism problem would have been solved earlier. But one cannot normally alter the concentration of the solvent and get meaningful data within the thing. So this is the possible mechanism for this occur process. So here first the PdCl4 is a palladium is a +2. So here the first the ethylene molecule is coordinated upon the substitution of the one chlorine. So to form this intermediate, next the water molecule is displaced another chlorine to form this intermediate, hydroxyl intermediate. Next, the attack of the nucleophilic attack by the water molecule on this ethylene carbon to form this intermediate. Next, the beta hydride elimination upon to form this acetaldehyde intermediate. So no deuterium is incorporated in the acetaldehyde when the reaction is carried out H2O, which could happen if the vinyl alcohol is released. So this must be another case in which the beta hydride elimination product never leaves the covalent sphere of the metal until it has a time to rearrange the metal by the multiple insertion elimination step. So this is the micro step. So here this is from upon the beta hydride elimination. This is from next the hydrogen inserted to this one to form this intermediate. Again the beta hydride elimination to form this acetaldehyde. So that proves that this intermediate is never dispatched from this metal center. That is rearrangement to the reagent happened in the metal coordination sphere. So the nucleophilic addition to the alkene complex give the vinyl metathesis, particularly the inserting variant of the reaction is addition electron containing 4 electron alkene. We can cis carbene. If the products are eta 1 vinyl, then the complex will be the 16 electron. So the theta T and theta 2 vinyl easily form. So the position of the nucleophilic attack in summary is usually that is predicted by the Green-Mango's rule. The upper process involves the electrophilic attack at the coordinated ethylene molecule. So thank you everyone.